Good afternoon, everyone. This is Niranjan Sitapure, and today I'll be talking about multi-scale CFD modeling and optimal control of continuous slug-flow crystallizer, specifically for quantum dot formation. This is the outline of the presentation that we are going to follow today. And first, I'll talk about some background and give you some introduction. Uh, Specifically, we'll ask the question why production of quantum dots is important and what are these properties that make them special. So to tell you briefly, perovskite quantum dots are nothing but semiconducting nanocrystals, which have very small sizes from 5 to 10 nanometers. They come in a variety of compounds, but specifically we'll talk about cesium lead bromides or cesium lead halides in this presentation and in this work. And they follow this nice perovskite crystal structure. Now, because of these structures and small sizes, they show something called as quantum confinement, which means that you can control the emission and absorption of these quantum dots based on the size. Also, they have very nice quantum efficiency and they are very luminous in nature. So you can see that they are very bright. Because of these, they find application in next generation displays and solar cells. For example, Samsung currently launched their quantum dot LED TV, which uses this technology and which has very wide color gamut and high luminosity. Also, in perovskite solar cells, these materials are used as functional layers, which are used to generate electron and hole pairs. And because of high quantum efficiency, you get much more efficient solar cells. However, all these amazing properties are effectively controlled by quantum dot size. Thus, efficient control of these quantum dot size is paramount and is at the center of this work. Um, this generates a certain motivation and certain challenges. Uh, so for size control, most of the people have been working on different synthesis methods, and most of these methods are batch synthesis methods, which have very low production capacity. They also have a lot of batch to batch variation, and they use very complicated synthesis methods. So that's why the industry market is lacking in these technologies. However, this brings a good opportunity for continuous crystallizers because you can make them at much higher flow rates. You can do active control like flow rate, concentration control. Also, you can scale them up very nicely. Specifically, in this work, we are going to look at slug flow crystallizers or SFCs because they combine the benefits of a batch crystallizer with a continuous one. And this is because in a SFC, there is formation of alternate liquid air slugs, and the crystallization of these small quantum dots occurs in these liquid slugs. And they are very well separated from other liquid slugs because of these gas bubbles. So there is very less axial dispersion, and hopefully you can have a better control. Furthermore, a CFD study also showed that the velocity profile shows that it is very well mixed in this small liquid slug. And that's why we hope that we can use this concept of combination of a batch and a continuous crystallizer to have better control. However, there are certain challenges in doing so. And majorly, these challenges are because of the slug formation process. Basically, there is a liquid there is a liquid slug, there is an air slug. They also have a vortex formation. So the combination of the turbulence, the surface tension effects, these in turn generates something called a slug-to-slug variation, which means that each liquid slug is a bit different from one another because of these stochastic concepts, you can say. And the mixing velocity in each of these slugs is slightly going to be different, which is going to affect the crystallization. Uh, Previous studies, both computational and experimental, they just fix the flow rate of liquid and gas, and they do not consider this slug variation, or it's very difficult to account for this. And that's why in this work, we want to address this issue and take it forward. That's why we are going to model slug flow crystallization to account for these effects. And the first thing we need to model is the slug formation. To do that, we did CFD modeling using ANSYS, and we used a volume of fluid method, which is very good to model two-phase flow. And the way the model works is you solve the Navier-Stokes equation for your air and for your liquid stream. You have a transport equation for your interface, and you can also consider the effect of surface tension because that can play a major role when you have organic solvents. Specifically, in this work, we consider a geometry as shown here, which is a millifluidic apparatus. And it is the same apparatus that we have in our experiment, so it is consistent. Here we have a liquid inlet where we inlet our precursor concentration for the crystallization, and we have a gas inlet, which in this case is a nitrogen. While simulating, you need to understand that this is a very complicated phenomena and you need to have a very fine mesh. So we did trial and error and tried different fine meshes to computationally be efficient as well as have detailed modeling. Here is an example of a particular fluid case where we can see the temporal evolution of slug formation. So here you can see that the air and liquid are entering the reactor, and as time proceeds, there is a nice alternate formation of air and liquid slugs. So you can see the liquid slug, the air slug, the liquid slug, the air slug, and this proceeds for an amount of time till you get a nice stable slug flow regime. However, it is important to understand that as you change the flow rate, there might be cases where you have an unstable slug flow. Basically, that the dynamics are too chaotic that there won't be a stable slug flow. On the other hand, for some cases, there will be a stable slug flow. So we need to do a grid search for different sets of fluid and liquid velocities so that we can find a stable slug flow regime. Furthermore, we try to quantify this stable slug flow regime by plotting the air volume fraction. And you can see that the air volume fraction in this case is 0, 1, 0, 1, 0, 1. So basically it's oscillating from liquid air, liquid air, liquid air slugs, which is what we want. Even if this is a very nice stable slug flow, when you plot the velocity of these slugs, you can see that there is a certain variation. And this is what I was talking about when I say slug flow variation. This is the variation and this is going to affect the crystallization. So to quantify this variation, we tried to plot it, and for us, fortunately, it fits a normal distribution. And now you can quantify this variation with the mean velocity and the standard deviation. And we analyze 500 slugs to present this work. Now you can extend this analysis throughout the range of your operation. So the crystallizer which we have operates in these gas velocities and liquid velocities, or these flow rates. And here we created a map or a lookup table of how the slug velocity varies, the standard deviation as well as the average slug velocity for these different fluid flow rates. Also, the white region here shows you that this is the region where there is no stable slug flow. So this table not only gives us the slug variation, but also tells us that this is the stable slug regime where we should operate our crystallizer. We finally validated our simulation model with experiments for the same geometry, and we realized that they are very in good agreement with each other, as you can see from this graph. Finally, now that we know how the slug formation occurs, we need to model the crystallization. So since I told you that each of these crystals can be considered as batch crystallizers, we write the concentration balance considering a batch system for each of these liquid slugs. Now, you have to consider the fact that these crystals grow at a certain growth rate. However, because this is a very new field of crystallization, the growth rate is not known. So in our previous work, we had developed a kinetic Monte Carlo model to find the crystal growth rate, which is based upon a ligand shell hypothesis. And you can read it in our previous work in detail. But basically what it says is that the crystal grows at a certain growth rate depending on the concentration, and there is certain ligand shell formation which stops its growth. We had previously validated our experimental model as well, and the experimental validation was very good. So we used the same previously developed model for a slug flow crystallizer. And we combined these two things to design an optimal operation problem for the slug flow crystallizer, where we concentrate on the set point deviation, the quantum dot size, and also minimize the variation or the crystal size distribution. Now this is subject to certain constraints. So I was talking about that the crystallizer should be in the stable slug flow regime. So that's a constraint. It also will have certain concentration constraints. Also, it is subject to the dynamics of the crystallization process. Now, because previously we had developed this for using a KMC simulation, which is very computationally expensive, we have used a neural network to mimic this expensive process, and we basically got the inputs from our high fidelity model, run it through a neural network to get a reduced order model or a very computationally efficient model for a crystal growth. So combining the neural network and the KMC simulation, we kind of get an optimal operation problem, which is now computationally inexpensive to minimize the variation of crystal growth and also have set point tracking. So here is a case study for the case of 9 nanometers, which is a set point, and minimize the distribution. So here you can see that crystal size varies with time. Initially it grows faster and then it saturates to 9 nanometers. So it has reached its set point. The crystal size distribution is presented in section B, and it has the deviation is around 5%. So given that the crystallization process is very stochastic in nature, also given that the slug variation is a very fundamental phenomenon, you can only minimize it, never completely let it go. Having this good set point tracking as well as excellent disturbance rejection is very commendable for this kind of an approach. Finally, to conclude and summarize our work, basically we have a CFD model which helps us model the slug flow variation and feed this variation data to a crystallizer model which uses a KMC simulation to finally give us crystal size distribution and crystal size evolution. We also have an optimal operation problem which minimizes the disturbances and ensures set point tracking for our quantum dots. And with this, I would like to end my presentation. Finally, I would like to thank all the attendees attending today, and I'll be very happy to take any questions if you have some.